Well, okay, a little more about this. Okay, so we've got these public parameters, we've got this modulus n, and we've got this v, which is s squared, the secret squared. Alice knows s. There's three things that happen, right? There's the first message, Alice chooses this random value. By sending the square of that, she's committed to r. She can't change her value r. That's the point. Bob sends his challenge, which is either 0 or 1, and then Alice responds with r times s to the e. Okay, and finally, Bob has to check whether this holds true or not. So does this prove it's really Alice? In other words, if everybody follows the rules, if Alice knows S and she follows the rules, the math all works, okay, but so what? Does it prove anything? In other words, if we put Trudy there, who does not know S, can Trudy break the protocol? That's our concern, right? Well, okay, so again, if everybody follows the protocol, well, it's fine. The math works, okay? But now suppose you're Trudy. You're sitting here and you don't know S. You can guess. You can make a guess. Is Bob going to choose E equals 0 or is he going to choose E equal 1? Suppose I guess. It's like the cave, right? If I guess that Bob's going to tell me to come out this side, I'm going to go down this side. If I think Bob's going to tell me to come out the other side, I'm going to go down that side. So suppose I guess, and I guess that Bob's going to choose E equals 0. Okay, and I'm Trudy, I don't know S. What should I do? Well, what do I send in the first message? R squared. I can do that. What do I send in the third message if Bob chooses E equals 0? R, I can do that. Hey, this is easy. I'll just follow the protocol. Okay, if I think Bob's going to choose E equals 0, I just follow the protocol. How about if I think Bob's going to choose E equal 1? Can I cheat in that case? Not if I follow the protocol, but I don't have to follow the protocol because I'm Trudy. Okay, so here's what I can do if I'm Trudy. If I expect that Bob's going to choose E equal 1, I'm going to still choose R, but instead of sending R squared in the first message, I'm going to send R squared times V inverse. V is public, right? And I can compute multiplicative inverses, mod n, easy. So I send that in the first message. And then in the third message, I send R. Okay, now what does Bob do? He checks that this equation holds true. Okay, he takes what showed up in the third message, he squares it, he gets R squared. He takes the first message, and he takes that times V to the first, right? Because E is 1. What is this times V to the first? It's R squared. R squared equals R squared. Okay, so I pass that iteration of the protocol. So the point is, if you're Bob, don't choose E equal 1 all the time. Okay, because Trudy can break it. Flip a coin. You really have to flip the coin, just like in the cave. Okay. Okay, so Trudy can break the protocol with probability 1/2. She could just guess whether Bob's going to choose E equal 0 or E equal 1. Okay, but again, it's the same problem. She can only do that with a probability 1/2. If Bob does it n consecutive times, her chance of guessing correctly every time is only 1 and 2 to the n. Assuming Bob really does flip a coin. So that says that E thing has to be random. Now another thing that's maybe not quite so obvious is the R that Alice chooses. That has to be chosen at random too. I mean, suppose that Alice gets lazy and she just chooses the same R every time. Why not? It's just, who cares? It's just a random value. Let's just choose the same value. Well, if that's the case, suppose Bob chooses E equals 0 the first time and E equal 1 the next time, and the same R is used. Okay, if you choose E equals 0, what do you send in the third message? You just send R. Okay, so now Trudy gets to see R. Okay, now if Bob chooses E equal 1, what gets sent in the third message? R times S. So Trudy knows R. She knows R times S. How can she get S? Don't say divide by R. Okay, we're talking mod n here. So you have to multiply by R inverse, right? So you multiply by R inverse, which is easy to find because you know R, right? So multiply this guy by R inverse and you get S. So if you get lazy, choose the same R, the protocol breaks, all right? Okay, so it seems to work. We can authenticate, we can prove that Alice knows the secret.
So
but
R has to be unique. You can never be
You know, yeah, okay, so it's sort of like your nonce or something like that. You know, if your nonce repeats and Trudy had saved up a whole bunch of nonces, she could replay, you know, that particular message. But the assumption is there's so many of them, it's never going to repeat. So just choose them at random and you'll be okay. Okay. Yeah, that's a good point. Okay, but there's something actually, you know, zero knowledge really it says something really strong. What it says is that people, you know, Trudy, Bob, anybody who observes this protocol learns nothing about the secret S. Now, that's pretty strong, okay? Is that really true? Well, you know, we're not going to prove it or anything like that, but, you know, we can sort of wave our hands at it a little bit here. From the protocol itself, there's some public information, right? S squared is public. Okay, can I get S from S squared? Why not? Because that requires a modular square root. How hard is that? It's as hard as factoring. Okay, so we can't do that. That's an assumption. We can't do that. That's too hard. Okay, so we can't get S from this. Okay, but Trudy gets to see R squared. That's always comes in message 1. And if E is equal to 1, in the third message, she gets to see R and S. Well, that's a lot of stuff, right? You get S squared, you get R squared, you get R times S. Why can't I get S from those things? Okay, what's missing here? Well, if I could get R, I could get S, right? Just take the multiplicative inverse. So I've got R squared here, so let's just take the square root and I'll get R. Oh wait, that's a hard problem, okay? Just as hard as this one. So I can't get R, I can't get S. So the point is there's really nothing in the protocol that seems to help you to break the protocol. I'm not really a proof of zero knowledge or anything. It doesn't seem to give you any helpful information. Okay, so is this just like fun and games for mathematicians? I mean, it is fun, for me at least. But no, it's actually potentially useful. Okay, now think about this. If you have an authentication protocol and you're relying on public keys, the first thing that happens in most of those protocols is you need to send your certificate, okay? Because the certificate contains your public key. What else is in a certificate? Other than the public key, what do you put in there? Your name, your identity, right? This says, hey, this is Amazon's certificate, and you send that. That's the first thing that happens. Okay, suppose you're Trudy now, and you're sitting here watching these messages go back and forth. You have no idea who it is until the certificates go by, and you say, oh, that's Alice talking to Bob. Okay, now I know who's talking. So you don't have any expectation of anonymity. You're not anonymous if you're using protocols that rely on certificates, because you send that information clearly. On the other hand, if you use zero knowledge proofs, it's just a bunch of numbers going back and forth to try and, you know, do this protocol. There's nothing in there that identifies this as Alice and this as Bob. So it's a way that you can potentially authenticate and remain anonymous. And it's actually used, I don't think we're going to have time probably to cover this, but Microsoft has, or at least had at one time, this concept for building a trusted operating system, meaning a small, secure operating system, sort of works alongside Windows. And as part of that, to make it secure, it has to do a lot of authentication. It has to authenticate all kinds of things, software, you know, devices, all sorts of stuff like that. And when it's doing this all the time, if you're using public keys, that could be identifying you. Okay, if you're using certificates, that could be identifying you and lots of stuff that you're doing. So they built into that support for zero knowledge proofs because it was a way to remain anonymous and get the authentication done. So it does have potential uses. And besides, it makes great test questions. So you know, it's got to be there. So. Okay, just kidding about the test questions. Okay, so another thing, so to finish up the chapter here, when we get to this point, something people used to always ask me was, okay, you know, you went through all these protocols, you know, symmetric keys, public keys, you know, nonces, timestamps, come on, just give me the best protocol. I don't want to mess around with all these different options and all that sort of stuff. But the trouble is there is no best protocol. I mean, it really depends on a lot of factors. You know, you could say the sensitivity of the application. In some cases, it might make sense to do something, you know, fairly simple, like look at, you know, the IP address and then use a password. And that could be a fairly simple protocol and might be usable in some cases. Delays or, you know, computational effort could actually be an issue. So do you want to use public keys? It's relatively costly computation-wise. How many messages are you willing to send? If you want to really decrease that, you better use timestamps. Otherwise, use nonces. You know, do you need mutual authentication? It's surprising how often you don't, in practice, need mutual authentication. You know, SSL, the most widely used security protocol in the world, you almost never do mutual authentication. You authenticate the server, and that's it. So that's all you need. That simplifies things. And you want some of that other fancy stuff like perfect forward secrecy, anonymity, and so there's a lot of factors to consider. The bottom line.